of absorbent flaking paints with methylcellulose and wheat starch paste.
Thank you for the kind introduction, Laura. As you can see, I'm presenting a study for the thickening of protein glues. At the beginning, I show you two examples of absorbent flakes. Here you see absorbent flaking paint on absorbent canvas, and here absorbent flakes of chalk ground due to delamination in the chalk ground itself. Protein glues, such as sturgeon glue and gelatins, are often used for readhesion. The advantage of these glues are their low viscosity and high cohesion. One of the main differences between the two proteins are their gel temperatures. A 5% solution of sturgeon glue gels approximately at 11 degrees, and gelatin with the same percentage has a much higher gel temperature, about 30 degrees, and therefore gels already at room temperature. How does this affect diffusion into the chalk ground and the adhesion? To see what is going on in the joint, both glues were fluorochromed and have a green fluorescence. The experimental setup was as follows. The glue was applied between two chalk ground layers, dried under pressure, cut in half, embedded, and the adhesive layer was investigated under the fluorescence microscope. And here are already then the results. The more green fluorescence you see, the more diffusion of the protein into the chalk ground occurred. For instance, sturgeon glue on the left side diffused completely into the flakes, providing neither a glue layer nor glue bridges in the delamination gap. Therefore, you see a black gap in the middle of the picture. Gelatin on the right side showed less diffusion into the chalk ground. One can even detect some glue bridges and therefore a slightly better adhesion, though the tested tensile strength was in both cases 0. To reduce the diffusion into the chalk ground and increase the adhesion, one should thicken the gelatin. This is often done in literature and in practice with wheat starch paste and methylcellulose. Here you see two different mixtures right after stirring and differences in the distribution of gelatin, it's still the green color, and the thickening agent. When mixed with wheat starch paste, gelatin is not entirely surrounded by the thickening agent. This is clearly visible at the edge where the gelatin is. In contrast with MC A4C 5%, the gelatin is dispersed in the gel, so at the edge there's no gelatin visible. Now the question is, how will this affect the diffusion of gelatin into the chalk ground? On the left, you see the diffusion of pure gelatin. That's our starting point, which we want in the first place to minimize, so to minimize the diffusion and gain a better adhesion. The wheat starch gelatin mixture on the right side did not prevent gelatin from diffusing into the chalk ground. However, there are more glue bridges, like we already know from gelatin. So the adhesion is higher, as the overall percentage is higher, but unfortunately the diffusion was not minimized. The MC gelatin mixture on the right generated the lowest diffusion into the chalk ground, generated glue bridges, and a good adhesion. Therefore, this is our favorite mixture. Now, let's have a closer look at the glue bridge between the two chalk ground flakes. You see the glue bridge and the gelatin inclusions, green dots, in the MC matrix, not visible. There is no continuous gelatin glue bridge between the chalk grounds. Is it possible to optimize now this mixture to generate a homogeneous gelatin bridge? We wanted to try this. And in order to investigate closer each component of the mixture, we fluorochromed both components with different dyes. The gelatin is now red and the MC green. Furthermore, we wanted to know how the mixture is performing when agitated under a paint flake, as we do it in the practice. The picture shows the application procedure. Here's the result. You see a glue bridge between the canvas with the isolation layer and the chalk ground. There are still gelatin inclusions in the MC continuous phase. The green color of the MC, the continuous phase, is hardly visible. But what we also see is that the isolation layer is green. This could mean that some part of MC diffused into it. However, still, there is no gelatin glue bridge between the chalk layers. So how could we achieve a gelatin glue bridge? The mixture should be able to separate so that the gelatin could accumulate. Hence, the MC gel should be less rigid. And this was also something we observed in our mixtures in the jar. The less rigid the MC gel, the faster the mixture separates. Therefore, we lowered the MC concentration from 5% to 3%. The ratio stayed the same. We gained a red-orange homogeneous adhesion bridge. It seems as if there is only gelatin in the bridge. We verified this also with FTIR FPA. The result was that there were no hydrocarbons in the glue bridge, and the bridge exists only of protein. Here the mixture separated and we gained a protein glue bridge with less diffusion of gelatin into the chalk ground than pure gelatin, additionally with almost the same adhesion as a mixture with gelatin and MC 5%, but a lower glue concentration. Now we have a concentration of 4, and a lower viscosity, which allows a better penetration under the flake. So, the conclusion. With that said, there are 4 results I'd like to conclude with, and please don't wonder, they will not appear on the slide. 1. We showed that there was less diffusion of gelatin into the chalk ground than in the case of sturgeon glue, because gelatin is a gel and gels at room temperature. 2. Thanks to thickening of the proteins, the adhesion was always higher. 3. We demonstrated big differences between the thickening agents. 4. Through the separation of the MC gelatin mixture, which usually is not intended, we succeeded in generating a homogeneous gelatin glue bridge. So the MC 3% transported the gelatin into the delamination gap, then diffused into the absorbent ground and flake or accumulated next to the gained gelatin bridges. So, for details, as I just presented the main idea, and for more information, please see the paper, and thank you for your attention.